one last one that I want to do here that I just think is interesting, and there's going to be a question like this on the assessment for my students in my classroom. I want to prove that secant squared of theta plus the cosecant squared of theta is equal to the secant squared of theta times the cosecant squared of theta, which, just pause for a minute, saying that something plus something is equal to that first thing times the second thing. And how many different unique numbers can you think of that that's true for? They don't have to be the same numbers, right? One of the easiest ones to do is if, right, like 2 plus 2, that's the same as 2 times 2. That turns out to be one of the cases that for a 45-degree angle, right, like the secant of 45 is 2 over root 2, or just the square root of 2. And the cosecant of 45 is also the square root of 2. So when I square them, I get 2. And so 2 plus 2 is 2 times 2. That happens at the 45-degree angle, or right, pi over 4. But this is just going to generate a list of numbers for which this is true always. Right? So I think that that's kind of cool. How I prove it, how I show that it's true, is when I'm in doubt, I change everything to sines and cosines, and that's, I think, the easiest way to go here. That secant squared is 1 over cosine squared of theta. Because secant is 1 over cosine, so secant squared is just secant times secant, which would be 1 over cosine times 1 over cosine, which would be 1 over cosine squared. You can make that jump, that right from secant squared to 1 over cosine squared. That's a reciprocal property. That will let me do this. I can do the same thing for cosecant. Cosecant squared is going to be 1 over sine squared. And now I have these fractions that do not have common denominators, so I think I want to make common denominators. This one is lacking a sine squared term. So I'm going to multiply that left side, top and bottom, by sine squared over sine squared. Pen is really not wanting to work very well right now. And this term over here is lacking a cosine squared. So I'm going to multiply top and bottom by cosine squared. I can do that because those are just big ones. So now this left term, I have sine squared on the top times 1 is just sine squared over sine squared times cosine squared. And this right term is 1 times cosine squared on top, or just cosine squared theta, all over the same denominator. So I'm going to put them together. That sine squared over sine squared plus cosine squared plus cosine squared over sine squared times cosine squared is just sine squared plus cosine squared all over sine squared times cosine squared. And this is my home base Pythagorean property, that sine squared plus cosine squared is just 1. I justify it here. From here, I'm basically there. I have sine squared and cosine squared in the denominator, which is 1 over sine squared is cosecant squared. 1 over cosine squared is secant squared. And I could show that. I could maybe split this apart. Say 1 is just 1 times 1. And I can associate, like, group these ones together and these ones together. But 1 over sine squared, that is cosecant squared. 1 over cosine squared is secant squared. And I'm there. So therefore, anytime I have an angle, if I take the secant squared of that angle and I add it to cosecant squared, that's the same as doing the secant squared times the cosecant squared. And yeah, like I said, for 45 degrees, that ends up just being root 2 squared is 2, root 2 squared is 2, so 2 plus 2 is the same as 2 times 2, but there's a whole list of other numbers that I could do. Secant squared of 45 is 2, cosecant squared of 45 is 2. But if I look at the 30, that's going to give me the same, like 30 degrees is one of our special angles too. I get 1 1/3 or 4/3, and the cosecant squared would be 4. That when I multiply those together, right, I'll just go over here, 4/3 times 4, that's going to be 16/3. But if I did 4/3 plus 4, I can't add the 4, I'd need to get a common denominator, so I'd multiply by 3/3. So that would be the same as 4/3 plus 12/3, which would be 16/3. 4/3 plus 4 is the same as 4/3 times 4, and I can find that number with those special angles in the secant squareds and cosecant squared lists. But that's not the only ones, right? Like I can do a bunch of different numbers all the way down that if I show this out, right, anytime you ever add secant squared plus cosecant squared, that's going to be the same as, I better change one of these to multiplication. Secant squared times cosecant squared. Okay. They end up being the same thing. 15 degrees, you end up with like 1.071 and 14.928, and they even end up being like nice clean numbers. It does the same thing for 22.5 degrees, that these end up being exact numbers with square roots in them, that when you square them it turns out that they're exactly this, but every time, right? You can make a list, you can do any random numbers you want. It will always give you two numbers that when you multiply them and when you add them, they make the exact same value. And I think that that's just pretty cool.